Welcome to the last half of the day of MACS 2016. My name is Steve Shaver and I'm the manager of service training, for those of you who haven't heard me say this like 8 times already. I'm the manager of service training for MACS Worldwide Mobile Air Conditioning Society, and I'm also the technical editor for our publications, such as Action Magazine, the monthly MACS service report, the MSR that we publish, and also our MACS WordPress blog. I hope you enjoyed all of the publications that we put together. A lot of time and effort and energy goes into writing the articles and producing the material for you guys as our members. And if you have any ideas, this is my selfish plug, if you have any ideas or topics I haven't done or you want to see me do, or something you want redone that we did before, send me an email and let me know, because we're always looking for more ideas. But especially if you ever have anything oddball come through your shop that you'd like to share with the rest of the MACS community, send it my way, because we try to throw them on our blog as much as we can. And you'd be surprised at the good feedback we get about stuff like that. It could be anything from a worn hose or to a clogged cabin air filter. They really, guys love to see stuff like that, so we appreciate that. So I'm going to introduce Tim. I have a little speech thing to read here. It's kind of short. Before I do my introduction. So this is Tim Iezzi. He's a working technician and co-owner of Iezzi's Auto Service in Reading, Pennsylvania. He graduated cum laude with honors from Elizabethtown College in 2011 with a Bachelor of Science degree in Mechanical Engineering. He currently holds ASC Master Technician certification, including C1, L1, and X1. He is a Pennsylvania State Safety and Emissions Inspector and a licensed repair technician, as well as a MACS Section 609 proctor. Incidentally, for those of you who teach 609 like me and Tim, we like to throw out little, tidbits of, fun facts kind of things. Like the 1 million tech certifications that we have. Well, one of them I throw out there is, 2 years ago, my son took 609 in my class at MACS, and I thought he would have been the youngest guy to ever get certified when he was 16 years old. Well, it turns out, if you go through the records, the youngest guy that we can find did his 609 class when he was 13. This is the guy. So, Tim and his family-owned shop have been MACS members since 1985. He currently holds the positions of Secretary and Delegate for AASP's Berks County Chapter number 23 of the Alliance of Automotive Service Providers of Pennsylvania. He enjoys racing, he's a fan of football, go Eagles, boo, and hockey, and his favorite car is the Superbird. So those of you who do follow us, follow our publications, probably have seen or heard of Tim or his shop. He graciously allows MACS to come in. He's only about an hour from our office. And when they're doing any special projects, we did an A6 compressor rebuild at his shop. He allows us to come in there, we get the story and the feature article. So, also Tim has been teaching for MACS for about a year and a half now. He became a proctor back in 2014. And last year he did his first annual Mobile AC Update. He did the 2015 Mobile AC Update with his AASP chapter. And today he's doing class number 2 in his inaugural debut at MACS. So welcome Tim Iezzi.
Okay, so today I'm going to do a bit of an introductory class on thermodynamics and how it applies to what we're doing in the bay with air conditioning systems and diagnosing what's wrong with them. If anyone needs pen and paper to take notes, there's some pens and some tablets up here next to the projector. If at any time you have any questions, comments, need clarification on something, just feel free to ask and we'll answer any questions from there. So what all are we going to cover? We're going to cover some background basics of thermodynamics, talk a little bit about the laws, types of heat, things like that. We're going to explore a little bit of the pressure-temperature relationships in an automotive air conditioning system and how we can exploit those relationships for diagnosis. And then if time permits, I'm going to talk a little bit about electronic variable displacement compressors, which is really the impetus of why we've had to re-examine some of these pressure-temperature relations, because systems behave a little bit differently. And we're also going to talk a little bit about diagnostic approach, how to make the most of the first few minutes that you're with the vehicle to gain diagnostic direction. We're not going to go into a whole lot of depth on the thermodynamic stuff. You're not solving equations of state and doing enthalpy and entropy calculations isn't going to help you fix a car that's in your bay, so we're not really going to go into much of that type of stuff. So first things first. Vehicle comes into the shop, you hook up manifold gauge set, system's running, and you see these pressures. About 38, 40 on the low side, about 90 on the high side. What do those gauges tell you?
Low charge.
Need some more information.
Yeah,
What
more
system we're
information.
working on, what's the ambient conditions, et cetera, et cetera.
Yeah. Yeah.
Exactly. What this shows us, it turns out on this particular vehicle, this vehicle is running, functioning normally at this point. What I want to get at is if you're only looking at pressure, you're only looking at half of the picture. You have to look at pressure and temperature together to get the full picture of what's going on in the system. In this case, I've had people say things like it has to be a low charge or a whole mess of other things. And it just turns out this big system is a variable displacement system. It's on low displacement. It's working quite normally. So basics. We're going to talk about the law of conservation of energy is an important one. Paul's favorite law. First law of thermodynamics. Energy cannot be created or destroyed, only changed and transferred. How I like to think about this is a vehicle going down the road, coming up to a stop sign. That vehicle moving down the road has tons and tons of kinetic energy. Kinetic energy is the energy of motion. In order to stop that vehicle, we have to change that kinetic energy into something else. Heat, we're going to apply the brakes, pass through the friction force between the pads and the rotors, or the drums and the shoes. We're going to turn that kinetic energy into heat energy. If we're using a low quality braking component, we're going to turn some of that into sound, where we get our squeal from. If you're driving a sprint cup car and going to turn one at Martinsville after 400 laps, you're going to turn some of that into light when the rotor starts. But that's all changing that kinetic energy into another form of energy. And that's what we're doing here with an air conditioning system. We are changing and moving that heat energy from the cabin out. Which comes into the second law that we're going to talk about, which is the work energy equivalence theorem. That means that what that says is that the changing energy of the system is equal to the work put into the system. We express that as Q out equals Q in plus work in. Q in thermodynamics is the symbol for heat. It is not H. H is a symbol for another one. So the heat out, what we remove from the system in heat at the condenser, is equal to the heat that we put into the system at the evaporator, plus the work that is put in at the compressor. Make sense?
Yep.
Everyone agree with that? So what is heat? Heat is energy. It is a physical quantity. We measure it in the English system, we measure it in British thermal units, BTUs. In the metric system, we measure it in the joule, is the unit. 1 British thermal unit is the amount of energy required to raise the temperature of 1 pound of water 1 degree at sea level, 1 degree Fahrenheit. The conversion to metric is approximately 1,055 joules to 1 BTU. So think about this as a pot of water boiling. As you're raising the temperature of that water, getting to the boiling point, you're putting more heat in, more heat in, more heat in, until you eventually boil. Every little bit of heat you're putting in is 1 BTU. Once you get enough of those in, the water boils. There's also two types of heat. We have sensible heat, which is the heat you can feel. You can feel the difference on your hand between 50 and 70 degrees. That's sensible. We can measure that with a thermometer. The other type of heat is the heat that we can't feel. That's latent heat. Latent heat is the amount of heat that it takes to change the state of matter. Meaning, you can't feel a difference, there's no difference in sensible heat between 212 degree water and 212 degree steam. The difference between them is the latent heat. In that case, going from water to steam, that's the latent heat of vaporization. How much heat has to be added or removed to change from a liquid to a vapor or back.
Which is the basis for air conditioning efficiency.
Exactly. That's what we're doing in air conditioning. We're not dealing in air conditioning with heat diffusion. That's going from solid to liquid. If you've got pad oil or refrigerant freezing in the system, you got bigger problems than anything that we're normally going to be dealing with. So like I said, the difference in that latent heat is the energy required to change the state. We have 5 phases of matter that we deal with in thermodynamics. Solid, liquid, and gas, which are your typical 3 states of matter. Then we have, in those latent heat phases, when we're adding or removing latent heat, we're not changing temperature, but we're changing state. We have the 2-phase solid liquid and 2-phase liquid vapor. Obviously in air conditioning we don't deal with the solid liquid, but we do deal with the liquid vapor. That's what we have going on in the condenser and inside the evaporator. Coming out of the condenser, we have subcooled liquid. That means that all the superheat has been removed. It's a pure liquid. Going in, we have superheated vapor. It means it's a pure vapor and there is no liquid. We have to make some assumptions that deal with an air conditioning system. These are very close to correct. They aren't exactly correct, but they're close enough that they work. The first one is that we're only going to transfer heat at the heat exchangers. Meaning, we're going to assume that there's no heat transfer going on through the lines, no heat transfer going on at the condenser, or at the compressor body, that we're only transferring heat at the condenser, the evaporator, and if applicable, an inline heat exchanger. It's not a bad assumption, because the air temperature in the engine compartment as it's running, with the hood closed, is pretty close to your compressor surface temperature, and is pretty close to the temperature of your high side lines. Not exactly great for the suction line, but it's close enough. We're going to assume that there is no pressure drop across the heat exchanger, or across any of the lines. Once again, it's not exactly accurate, and I have examples that we can show that, but not every vehicle are you going to be able to measure pressure across each heat exchanger or pressure in every line. If you can't make exact pressure measurements in every line, either with a gauge setter or a transducer or something, you can assume that the pressure in the high side of the system is constant and that the pressure in the low side of the system is constant. Not exactly right, but it works well enough. The third assumption that we're going to make is that the working fluid is a pure fluid, meaning solely R12, solely R134A, solely light. Once again, not exactly right because there is pad oil in the floating around in the system, or mineral oil, or coal oil, and there's a little bit of moisture. Not exactly right, but it's close enough. It's also important to remember that heat always travels from areas of highest concentration to lowest concentration. That's the direction of flow. You're not taking cold air and pushing it into the cabin, you're removing heat from the cabin. In thermodynamics, there is no such thing as cold. Cold is only a lack of heat. We only talk about heat. Cold is not a physical quantity. So the name of the game here in automotive air conditioning is vapor compression refrigeration. Our basic system, we have a compressor. The refrigerant leaves the compressor as high pressure vapor into the condenser, leaves the condenser as a high pressure, high temperature liquid. Through the expansion valve, it expands low pressure, low temperature into the evaporator. The refrigerant boils, transfers heat from the air, leaves the evaporator as a low pressure, low temperature vapor into the compressor, and the cycle starts again. This chart is called a pH diagram. We have absolute pressure on the vertical axis and enthalpy H on the horizontal axis. Enthalpy is a quantity that takes into account the internal energy of the refrigerant as well as some other things. Not going to go into it because it doesn't play into anything that we do in the shop. What is important from this diagram, what this diagram shows you, is all these lines that come in, come down straight across, and go like this, are lines of constant temperature. We have pressure going across, temperature coming in like this. What these curves in the center are, they define the regions of this chart. So over here on the left-hand side, we have all the pressure and temperature combinations where the refrigerant is a liquid. In the center, we have all the possible pressure and temperature combinations where the refrigerant is a liquid and a vapor in the two-phase. And on the right-hand side, we have all the possible combinations where it is superheated vapor. If we plot an ideal refrigeration cycle on this diagram, we have something that looks like this. This would be ideal. At this point here, that would be our compressor outlet. Just barely superheated vapor, high pressure, high temperature. Come across, condense that, turn it all into a liquid, just barely subcooled, high pressure, high temperature. Go through the expansion valve, through the evaporator, leave the evaporator as low pressure, low temperature, just barely superheated, and back to the compressor and start all over again. An actual system looks something more like this. My favorite saying is there's absolutely nothing ideal about anything in the automotive. We don't deal with ideal. So you can see we leave here, we wind up further into superheat, further into superheat, further into subcool, and closer to subcool. It's basically a bigger traffic. What is often done in a thermodynamics text, just for ease, is we take this information out of a graph and put it into chart form. Makes it a little bit easier to find what you need. This chart is what's in the middle of that graph, in the two-phase region. I want you to take a look at these two columns. Richard, what do these two columns look a lot like? Something we've all seen before.
The pressure temperature relationship between refrigerants.
Yep, that would be what we would consider a pressure temperature chart. It's important to notice, to remember, look at that chart, and let's look at this graph. What that chart is the middle region here in the two-phase. That's the only place where that pressure temperature chart holds, is when you have a liquid refrigerant and a vapor refrigerant existing at the same time. So it's important to remember that that pressure temperature chart is not the golden rule when you're doing temperature testing. That the relationship that you have on there is not always going to hold. On a fixed displacement system, it is very close. As a general rule, what you're going to have, if we go back, is your condenser inlet temperature is going to be higher than what the PT chart says it should be for a given pressure. And your outlet is going to be low, because we're working outside of this two-phase region. We're into vapor and we're into liquid. So let's look at a real car. Let's evaluate this a little bit. Vehicle in question was a 2013 Kia Optima, electronic clutchless variable displacement compressor. This particular vehicle, we were able to measure high side pressure in the discharge line, low side pressure in the suction line. And this particular vehicle also had a pressure transducer in the liquid line, so we were able to measure pressure in and out of the condenser to do testing. The vehicle is also equipped with an inline heat exchanger. Now, Alan talked in his presentation at lunch about what's going on with inline heat exchangers. All photos, all the pictures in this section are courtesy of MACS. They did the testing with Steve and Richard and Dennis last year. So here's our setup. We're using these temp scans with the thermocouples to measure our temperatures. We have a tool here connected in line in the circuit to the compressor with measuring the duty cycle of the compressor because it is electronic variable displacement. And we need to know what we're commanding to. What is the PCM looking for? Also have the voltmeter here measuring the voltage to the compressor. Some up close shots there. On the triple R machine measuring high side and low side pressure. And the scan tool up at the top measuring the pressure in the liquid line off of the pressure transducer out of the PCM data set. Important tip, if there is a pressure transducer in line when you're trying to find another pressure measurement, you can look in data stream and see if it's given. What I have found looking at vehicles is a lot of times, if there is a pressure transducer being used, it's in the line that does not have the high side service port. So you often can measure both pressure in the discharge and in the liquid. So let's see what we got here. With the system running, we're in about an 85-degree shot. System had been running about a minute. 175 psi gauge on the discharge line. About 160 in the liquid line. About 50 in the suction line. The condenser inlet temperature was measured at 163 degrees. The outlet temperature measured at 103 degrees, which is also the inlet to the inline heat exchanger. Outlet of the inline heat exchanger is measured at 99 degrees. Outlet of the evaporator measured at 49 degrees. And the compressor measured at 80 degrees. Duct temp of 59 degrees. Like I said, this was just, the system had been only running about a minute at this point, and it was running on maximum displacement. So let's look at some key points here. What jumps out at you?
60 degrees, the difference with that condenser.
Yep. That's the biggest thing. That's what should jump out at you. We have a large temperature drop across the condenser. Now, this particular vehicle was working. It was a rental car, didn't have a whole lot of miles on it. Air conditioning was functioning well. Normally, we would say, oh, we got a 60-degree drop across the condenser. We have a blocked condenser. There has to be something going on here. Let's take a look at it. Let's look at the math here. So one other thing to note here when you're looking at anything chart-wise or table-wise in thermodynamics, all of your pressures will always be given in absolute pressure. You don't deal in gauge pressure in thermodynamics. So to go from what we measured on a gauge set to what your chart is going to be in, add 15 psi to it. The difference is atmospheric pressure, which is 14.7 psi. Add 15, it gets you close enough for our purposes. So here we've got discharge, 175 psi, 190 absolute, 163 degrees of temp. Idle. This is all done at idle. So we're going to look at some charts here. All these charts were compiled by the textbook authors from that pH chart that I showed before. One thing you see a lot in these charts, they don't cover every possible temperature and pressure, it just runs out of space. So you wind up kind of doing an interpolation, going and doing the math, and then all the relationships are linear. So we'll split the difference here. We're looking for 190, the charges are 180 and 200. What we're looking at here with all of these columns up and down are physical properties of the refrigerant at a given pressure and temperature. We don't really care about any of those properties for our purposes. What I want to look at here is what the saturation temperature is, and it gives us a rough idea how far into superheat we are, how superheated that refrigerant is. So if we look here, if we were at 180 psi, absolute, our saturation temperature is about 118 degrees. Or at 200, our saturation temperature is about 125. So any temperature above that we measure, the refrigerant is superheated, it is a vapor. So we measured our temperature at 163 degrees. Our saturation temperature, if we split those, is about 121 degrees. So we are very, very, very far superheated when we're looking at this system. You know, we're almost 40 degrees above our saturation temperature. We'd be down here somewhere on the chart. Let's go for the outlet. 160. What? Yeah, 103 degrees. Now I made a mistake here when I was doing the presentation. I have 160 psi absolute here. It should be 175, but it's still the point still comes across, because even though that's a lower pressure than what we actually have, the saturation temperature is still above what our temperature is. So that tells us that the refrigerant coming out of the condenser is a pure liquid. It is very far subcooled. So what that tells us is that condenser just pulled a whole lot of heat out of that refrigerant, and the condenser is doing its job and it's working properly, even with that 60-degree temperature drop. Everyone cool with that? Makes sense? Any questions? I have some theories on that I'll get to in a little bit, Paul. Let's look at the evaporator. So our temperature, our low side was 50 psi. The evaporator outlet was 49 degrees. So do the same thing. Our absolute pressure would be about 65. Split this in the middle. Our saturation temperature there would be about 54 degrees. So what's interesting here then, though, we have liquid by the temperatures coming out of this evaporator until we go into the inline heat exchanger. What this vehicle is doing, the final boiling of the refrigerant is happening inside the inline heat exchanger. It's not happening in the evaporator. The inline heat exchanger is functioning similar to an accumulator. Yes?
If I understand right, that would mean we can flood the evaporator more with the internal heat exchanger.
Yep. Basically, this vehicle is acting more towards like what a CCOT system will do, where we're using this as an accumulator, letting the refrigerant boil out. And we're doing it to improve our efficiency at that point, because then we can put colder refrigerant, or refrigerant that has more capacity to take heat into the evaporator, because we're taking some of that heat out in the inline heat exchanger. Make sense?
Yeah, that's exactly.
Yep.
So they're deliberately flooding the evaporator with more liquid to let more liquid pass on through. And the inline heat exchanger, which
Yep.
Would it be a correct statement to say that the old school way of doing it with the superheat numbers on those valves was basically giving up some efficiency to make sure you prevent liquids slugging in a compressor. It actually gave up some internal efficiency of removing heat from the vehicle to make the system work without damage. But now with the new system design, we can basically do what we used to do with the work scoop, right? That's what I was hearing you guys say earlier. Where we used to float a little bit more and rely on the accumulator. Now that dual line exchanger is performing what the accumulator used to do for us.
I think that's what the numbers have showed, that basically I believe that to be a correct statement. Because yeah, you know, with just an expansion valve and not having an accumulator in the summertime, you have to make sure that expansion valve is working such that you only have vapor coming out of the evaporator. We know what happens when you put liquid into a compressor, the pistons come out the side of the case. So,
Well, that's why they, when they switched, when they came in with the orifice tube and accumulator system, that was why you could flood the evaporator, but you had to get rid of any liquid, you still do, and the accumulator, the accumulator is basically a liquid trap.
yep.
Yeah. Do you have a temperature where the return is coming out of the inline heat exchanger?
Be the return line,
Somewhere.
the line to the between the inline heat exchanger and the compressor, 80 degrees.
So there's where she shot it back.
Yep, exactly. So,
Well, I just want to say that I have a new set of gauges I just got that it has two thermocouples built into it. It'll calculate the saturation point and the superheat and subcooling of both sides. And it makes it nice where you don't have to now use charts anymore, and it's all instantaneous for you.
okay, I didn't know that.
Yeah, it's all programmed in. It works out really nice.
Okay, I didn't know there was a product available.
Yeah, just for doing stuff like this.
Okay. So now let's look at this system. Now that at this point, when these pictures were taken, the system had been running for quite some time. We had the vehicle running about half an hour. All of our testing we did at this point, we were doing on high-low where we start engine at up. So at this point, it had been running about half an hour. The cabin was cool. And we can see the PCM has turned the duty cycle of the compressor back from running on full displacement. Now we're running about 42% displacement. So let's take a look at some numbers with running on a lower displacement. You can see where our pressures were and some temperatures. So we had high side of about 120 psi, liquid about 110, 42 psi at low side, 125 degree condenser inlet, 90 degree outlet, 71 degree evaporator inlet, or expansion valve inlet, I should say, 47 degree evaporator outlet, 75 degree condenser inlet, or compressor, compressor.
Now, in the normal range, condenser,
Yep.
deltas.
Yep. And we've got, like I said, center dock temperature 47 degrees. Car had been running about half an hour. The cabin was cool. So let's go back and do the same thing. 135 psi absolute. Split that along the middle. Saturation temperature would be about 97, 98 degrees. Was our temperature 125? Once again, we can see we're very superheated coming in. Not quite as superheated as we were before, but we're still a rather large amount of superheat there. Condenser outlet, 125 psi absolute, 90 degrees. So our saturation temperature there would be about 92, 93. Okay, we're good. We have liquid coming out. Evaporator, we have 42 psi, 47 degrees. So now, as Paul said, when we are dealing with these systems on maximum displacement, we're having much higher temperature split than what we're used to. Much more, for years we've been told 40 to 50 degrees across the condenser. Any more than that, you have a restriction somewhere. We've just shown that doesn't hold on this vehicle. We've seen on these clutchless variable displacements, or electronic variable displacement systems, 80, 90, 100 degree drops across the condenser with the system functioning perfectly normal. So why? And how can we use this to figure out if we have airflow restriction or if we have a blocked condenser, since the old rules of thumb really no longer apply?
Well, we're sending, unless I'm missing something, and say I'm barely late at this point, Tim. We're taking a lot of, we're taking the low temperature suction side and we're warming it up very considerably.
Yep.
So that can account for some of the higher discharge temperature.
We have seen this also on vehicles that don't have an inline heat exchanger. I know we had looked at a Chrysler product 2 years ago that did not have an inline heat exchanger, and we're still seeing similar temperature. Well, my thoughts on it,
Which Chrysler product?
I don't remember.
Because the Caliber and Compass had a complex strategy of calculating cooling level.
I know it wasn't one of them. I know it was a cheap product. I think it was a Liberty.
I had no idea. So the only thing I can think of offhand.
Yeah.
Those two vehicles.
Yeah, I don't remember what exact model it was, but what my thought on it is that at all times as this system is running, we have to make sure that we have vapor in and vapor out of the compressor, vapor in and liquid out of the condenser. Otherwise, the system doesn't work. So at low displacement, if we go back to up here to discharge, at low displacement, our system looks something like this, which is kind of what we're used to. As we change the displacement, up the displacement, we're coming out to here, and getting further and further away from ideal. My thought is that the system has to have enough capacity to transfer heat at max displacement and yet still make sure we're working at minimum displacement. So we're transferring more heat out. I don't think I'm saying this right, but that in order for it to work and function normally at low displacement, we're moving so far from ideal at higher displacements that the temperature drops and everything that we're used to seeing just don't happen. That we're winding up transferring a lot more heat than is expected. I don't know if that's right or not, but I think
the only thing that bothers me about that is how are we making the changes? We can reduce the flow into the condenser, and maybe it's somewhere by changing displacement. And maybe it's somewhere in there. That's all I can think of. If you've got some better ideas.
yeah. So unfortunately, we really don't know 100% why this is happening other than it does. And it has to deal with the superheat and heat transfer.
Did I understand you correctly that these measurements were taken while you were intrusive in the system? You were commanding the state of operation of the compressor?
No. This was what that tool that's shown there.
You're just letting it ride on its own?
Yeah, this tool is capable of changing
Of doing it for
the compressor displacement, but all that it's set up now is a little bit hard to see, but at the top there, it says normal mode. So all that this is doing right now is measuring what the duty cycle is.
Yeah,
So you could have done this with the scan tool and just watch the...
Exactly. Actually, we tried to do it with the skin tool. This vehicle did not support any compressor control pins with the skin tool. We couldn't monitor it that way. But But you can do it, you can just as easily monitor it with a lab scope or something like that. Anything that can measure your duty cycle. That's basically all we're doing with the compressor testing tool. We're not actually commanding anything.
You just read past it.
Exactly, it's just a pass-through, not actually changing anything.
Yeah, that's the only one that we use straight pass.
Yep,
The other one is a command tool only.
yep. Yeah, this one can do straight pass. So now, unfortunately, I haven't had one of these vehicles in the shop yet that had a blocked condenser, so I can't tell you exactly what you're going to see if you come up with a vehicle that has a blocked condenser. What you're going to be seeing, for an airflow issue or a heat transfer issue, is similar to what we've always seen in that you're not going to have as much temperature drop, and what you're going to see if you look at the charts, if you plot the pressure and the temperature, you're going to see that the temperature coming out of on the condenser outlet is either at the saturation temperature or above it, indicating that you still have vapor coming out of the condenser, that you're not condensing all of the refrigerant.
Tim, what, just, maybe it didn't occur to you or you didn't have time, whatever, but when this occurred, we had a huge temperature drop. Couldn't you have just simply at that point locked or turned off the fan, disconnected the fan or blocked the condenser, see what happened?
We did. We actually kind of made a mistake when we were, at one point while we were testing this. We weren't using that compressor testing tool to see what would happen when we were in manual control. And someone who shall remain nameless didn't turn the actual air conditioning system on, so the cooling fans weren't running. We had a compressor running at maximum displacement, no fans. Everything started changing so rapidly we couldn't get any numbers to see what was going on, because we hit about 400 psi and turned the ignition switch off very rapidly. This system was capable of making a lot of pressure very
So
fast.
we don't know what would happen.
So we unfortunately, we weren't expecting it, so we weren't ready to take measurements, and we didn't.
Yeah, well, that would be really interesting to see what, that would give you a clue as to, if we block the airflow, that would, tell you something.
That's something I do. I have all of these tools at my disposal, so when I get one of these vehicles in the shop and I have some time over the summer, that's something I'll probably play with. See what does happen exactly if we have an airflow issue. But that is not something we have as of yet tested.
Yeah, I don't know how you do the lock.
Yeah, I was talking to Steve some time ago. We were trying to figure out how we could do that and haven't yet come up with it.
Non-invasive.
Yeah.
You can do it lots of ways, like a big pair of pliers.
Actually, we tried that on his Jeep at one point, and it didn't work real well. Trying to just print tubes.
Yeah.
That didn't work real well. What you wind up having basically is make a blocked condenser, cut the end tank off, weld tubes shut, or block tubes, and weld the end tank.
Well, you could get like you familiar with the lock rings? Yeah, if you took a lock ring, put some sort of restrictor in that, and then just replace the lock ring when you have another real one, that'd be probably, you gotta do it in basic.
Yeah.
That might be something, at least repairable,
Yeah.
without going crazy.
That's definitely something we'll have to look into. Do it all. So let's talk a little bit.
Thank you.
I think Richard volunteered at his Astrovan for that.
Well, anybody's got an afterman who'll volunteer for anything.
Okay, so let's talk a little bit about these electronic variable displacements. Since these systems behaving differently is kind of why we're looking at temperature testing in a new light. So how does it work? As Alan said in his presentation over lunch, we have pulse width modulated duty cycle solenoid in the compressor that changes the pressure inside of the compressor to move the slosh plate. Basically for all intents and purposes for what we're doing, these compressors are basically take a GMV5 that we've been dealing with since the 80s, take out that mechanical compressor control valve, and put in a duty cycle solenoid. And that's what you've got. These compressors may or may not have a clutch. The manufacturers are tending back towards putting clutches on them. so that the compressor can be disconnected. Most of what's coming through newer, like Alan said, Chryslers gone back to putting a clutch on their compressors.
Everybody over the years, we all talk about that. One of the problems they had with the variable displacement compressors was that when they started trying to run them down to zero, as close to zero cooling load, you have to run a certain amount of bias so that if the cooling load changes, you can kick the compressor on again. And Nissan had a lot of problems where they kept on the highway run, particularly if you were doing if it was minimum cooling load, they would go into like 3% or 2% balance. It was 3% balance position, 5%, something like that, and they couldn't come out of it. They sort of stuck there. So they had to change that and get more bias into the thing, and that sort of cut a lot of the economy advantage in the thing. Limited, but whatever.
The other thing we run into on something that was prevalent, if you looked under the hood of like a Jeep Compass or one of Chrysler's early clutchless electronic variable displacement systems, there's a note on a ring around one of the service ports to not run the vehicle if the system's in a vacuum, if there's no pressure in the air conditioning system. Since it couldn't be shut off, it was possible to pull the oil out of the compressor and starve the compressor for oil and do compressor damage. Another reason why the manufacturers are going back to clutch. Now the compressor can be disconnected mechanically from the belt drive.
My shop has seen nothing but failure from the ones that are clutchless. If they've been in an accident that was major enough to lose the refrigerant, but not enough that they could continue to drive it, they took out a compressor every time.
We've seen that as well from some of
That's
the
only failure on the clutchless that I have seen so far.
Yeah, and the theory was that once that thing fractured, let the belt continue to run, they could save the compressor. They won't save the compressor.
No. Next. So we've got we have a PCM control compressor that we're not controlling cycle, we're controlling duty cycle. So what we need to know in order to test these systems, what is the PCM looking at? How is it deciding where to put the slosh pole? I have a chart here that was presented in a presentation at this convention last year from Peter Bradley with Barrichello. These are some of what Volkswagen is using to run their compressor. And if you look at most of what the criteria are, it's the same kind of criteria that we've been using to cycle the compressor for years. Okay, we're going to under what conditions are we going to turn the compressor off or turn the flow out? High pressure, obviously. We always cycle the clutch on high pressure so we can open the pop off. Low flow, low pressure. Don't want to freeze that evaporator up. Economy mode, low outside temperature, high engine temperature, wide open throttle, low voltage, and system faults. Or if the compressor is consuming too much power, we're about to lock up and disengage the clutch. So what do we need to know about these to diagnose them? If we have a problem with a vehicle equipped with one of these compressors. Well, as we've already discussed, your temperature changes are going to be different. The old rules of thumb don't apply to temperature testing. And diagnosis for these vehicles is going to be more scan tool and lab scope dependent. You're going to have to be able to check and see if that solenoid is doing what it's being told to do with a lab scope, see what your duty cycle is going to the solenoid actually is. You need to use a scan tool to see what it's commanded to, if you can, if that's available in gauge. And you need the scan tool to look at the inputs, see why the PCM is deciding to do what it's doing. Some of these vehicles may set diagnostic trouble codes for solenoid issues. I had, in my morning class this morning, I had a gentleman that worked at a Cadillac dealership. He said what he has found is the Cadillacs and their automatic temperature control system had a very high likelihood of setting a trouble code if anything changed in the solenoid if the compressor wasn't doing exactly what it was told to. Same compressor in something like a Chevy Sonic with a manual temperature control system, they don't set trouble codes. Almost never have.
In Chrysler, they only set open or short.
And this Kia that we were testing, it had the capability to set open and short circuit codes. We couldn't get them to set. We tried.
Oh.
You know, we were running with the compressor unplugged. It would not set an open circuit code. So I'm not sure what's going on there, though. Like I said, it was listed in the DTC chart for the vehicle.
It may have had, one thing, unless you get the actual algorithm of the code, it may be more than just.
And unfortunately, we didn't have the code set criteria
Yeah.
in the service manual for that vehicle.
Yeah. The manual sucked.
No comment.
Unless they've improved, they really were bad.
They're not as bad as they used to be.
Oh, okay.
But
Once they started charging, I stopped looking. They used to have it free.
Yep.
Not anymore.
not anymore, no.
Yeah.
So, like I said, yeah, our diagnosis on these vehicles is going to be more lab scope and scan tool heavy than in the past. Along those lines, yeah, everyone has a different procedure for what they do when a vehicle comes into the shop with an air conditioning problem. And there is no wrong or right way to the other. What you do to start is really up to you. I get a lot of questions asked me when I'm teaching as I've been teaching section 6 and 9 classes last year. It comes up a lot. What do you do? How do you start? So let me throw it back at you. What do you do when a vehicle comes into your bay with an open complaint? What's your first step?
I usually talk to the customer as much as input as I can. Just try to get all the information that I can. What was happening? How long has it happened? What was the first thing you noticed? Did you hear anything?
But okay, so say we've done that. The service writer did their job at write-up, got all that information for you. You're the tech. You're walking out to the vehicle, pulling it into the shop. What's the first thing you do once you approach that vehicle?
I'm going to see if the clutch is even engaging. Just a visual. Look at the system. See if it's got all the caps on it. Has somebody else been messing with this? Just reach down and fill up your hoses. The simple things that you can do before you even hook up.
Okay, how about you, Richard?
Pretty much what he,
Okay. That's a good first step. But my first step is, or your first step should always be, verify the customer complaint. As I'm pulling this car into the shop, I walked out to the vehicle, start the key. I like to go through, I check all my blower speeds. Do I have all my blower speeds? Do I have all my modes? Can I feel a change in temperature as I move the blend door? Does the blend door, do I hear the blend door move? Verify the complaint with either no heat or no cold. Running it into the shop for a minute, you're not going to get a whole lot of heat, but you should be able to feel the difference between hot and cold at that point in time. Same thing with cooling. Now we've verified, okay, the air conditioner is not cooling, open the hood. Yeah, we're doing our visual look around, looking for the obvious. Is the belt there? Is the clutch there? Is everything there? Did the belt rub through a suction hose? Did the belt rub through something? Did I have a rock go through the condenser? Then I've got two important steps that most people miss. And that's before I hook up any test equipment, do any tests, I want to know, does the system have sealer in it? And is the refrigerant pure? Because if the system has sealer in it and fails a sealer test, or it's not pure, I'm done. I have no interest in contaminating my equipment. Contaminated R134A is expensive as all get out to get rid of. Once we've established it's pure, I'm going to hook up my manifold gauge set, see do I have refrigerant in the system. Start the car, is the clutch engaged, is my suction line cold. Try to figure out if I'm headed looking for a refrigeration circuit problem, a control circuit problem, or something in the dash. And you can do the same thing with a no heat issue. Start the car up. Is the belt still there? Because obviously you're not going to have heat if you don't have a water pump turning. Is the cooling system full?
Gee,
Yeah, you lose that water pump belt, you've got,
No,
more
no,
problems.
no water pump valve.
Yep, the timing chain, yep.
Yeah. I never had that go on my old one.
Feel around, are the heater hoses hot? Same deal, does my control system work? Figure out in the first 5 minutes, you can get a sense of where you're headed to try to make your diagnostic time as fast as we can. Develop yourself a plan of attack that we follow this plan for the first few minutes on every car that comes in the shop to minimize going in the wrong direction. There's no point in chasing a control system problem if you have a refrigerant leak. Same deal, there's no point in chasing a refrigerant leak if your problem is the control circuit that the compressor not engaging. You can replace all the compressors that you want to for a compressor not engaging, and it's not going to fix the power wire that's rubbed through under the battery tray. Any questions? If there's no questions, then that's all I have for you guys today.
I think we all learned a lot about with that, with the, variables. I don't think any of us will do that. By the way, I just, you always do a check the seal.
Yes.
And you can find, in other words, there's being two types. And you can find a lot of stuff, but I'm just, your experience.
No. Part of that is, I think my experience with that I don't find a lot of stuff is the reputation that my shop has. We have a reputation of being expensive. So the people that are generally looking for the $50 B&AC Pro with this magic can that Advanced Auto Parts sells aren't normally coming into my shop. So that isn't something that we see a whole lot. I have seen it in the past. The best one that I've ever seen as far as sealer had a girl, worked at parts store whose first name starts with auto and ends with a Z. Late 2000s Jeep product. Air conditioning didn't work. One of her coworkers decided it needed a compressor for some reason. Don't know why. Hung a compressor on it. Charged it, and those vehicles held 1.25 pounds of 134, a very small system. Somehow got 3 cans of 134A with leak sealer in. This thing was so bad, it plugged the orifice on the sealer tester instantly. You would just see a pressure spike and a spike on the flow meter and down, and you can see the hardened sealer inside the plug. As soon as the clutch engaged, the compressor went into high pressure lockup and blew the pop-off valve faster than the clutch could disengage.
Wow.
It was that overcharged and that much secret. To date, that's the worst I've ever seen.
I'm guessing a lot of people, when I enter a refrigerator, just find the refrigerator with seal.
That is one thing also, you get the, what we tend to see more is the people that are cheap and decide to top it off themselves, don't want to spend the extra $2 for the can that's got stopped.
Oh.
But then just buy the straight refrigerator.
I would think it would be, they'd say, oh, I'll get some stop, they can stop the leaking too.
Well, they push it when you're in the auto parts places. I've been,
Yeah.
I've been
you got
standing,
these
standing there in
I'll
line.
get it with the sealer so you'll stop.
Some of them, that's all they have.
Yeah, for any cases, yeah.
What did that girl end up doing with the car?
No clue, didn't want to spend the $3,500 I quoted to replace the air conditioning system. Yeah, that's a case of, with Sealer, Chrysler has a service bulletin now that it did apply to that vehicle. They never updated the bulletin to apply to newer vehicles. I forget where it stops application-wise. But that states that if there is sealer in the system, treat the system as contaminated, do not attempt to flush it. You can't flush the sealer out. Replace every part down to the last pressure switch.
If the refrigerant is removed, you're probably gonna be okay. I know that, I've had students that have, and I tell them I can't touch it if there's refrigerant in there. And seriously, they come back with no refrigerant. And I can charge it up and fix whatever problem they have. But, and I have a couple technicians that have had sealant brought in. They bought a used vehicle, didn't realize it had sealant in it.
You're correct.
We found it in the past.
I'm not going to disagree that you're probably okay, but I am going to say that it's best to follow the manufacturer's
Yeah, I
document.
understand. Yeah, for a customer,
Yeah, if it was my own car, I might try to do something.
If you're not gonna warranty it.
Yeah, exactly.
If you
This is the
want to-
customer.
Yeah, you're not gonna want to.
Done mistake of putting in the sealer.
Yeah, but say if it was a case where I bought a car or something like that. In my own car, I might try something. I'm not gonna put my name and my reputation on patching someone else's mistake, is what it boils down to.
Yeah. Nice presentation.
Thank you, Paul.
So I had a picture of one of those games back in '71. I don't have this one, but it's similar. So it shows you, you got your high pressure and low pressure, but then you have your saturating temperature based on those pressures. And then you use your superheat values and your stuff too.
Okay, so that's something more Gabe said that's geared towards
Residential.
residential HVAC.
But
That's what-
it's doing the exact same thing.
Yeah.
Up there.
Okay.
So, you know, it's
Don't have to do it.
What's not, what I've done is I'm not looking up in the chart to try to figure stuff out. So
Yeah.
I can ready to go from there.
I can see that actually being a very, very useful tool for us, and that is
It's not really
something.
measuring the temperature though, right? It's just converting.
No, it's measuring.
Based off the pressure, right?
No, you actually have thermocouples in there. So you actually have you can't do it without the thermocouple. So you have a thermocoupler on the suction line and then on the liquid line.
Because I mean, some of the older gauges do have temperature based, they're based on pressure.
Yeah, so no, it's actually measuring temperature.
I haven't used them enough. So notice that, thinking with the last one, I'm doing work on the house, just doing testing, unless I've got something that's really odd,
Well, I like that call.
or that I'll look at specifically for a product, normally there's anything I
I
need.
switch over to our phone.
Richard has a lot more experience with touchscreens than I do.
I mean, some of those gauges you still have,
And a lot of the global
Yeah.
is very similar to it.
temperature behind the pressure.
Yeah.
Both of them.
But it's
Basically, the
yeah,
temperature is very minor.
chart. So
We'll
it's-
see if I did
Yeah,
that
exactly.
rather
If I
than.
don't trust the town, I got a
But-
problem with that.
And it should be pretty accurate.